So I am the only face that's visible.
Yeah, I think we can turn our video cameras as well. Otherwise, it seems like a team.
Seems too mechanical. Right.
I'm talking to some dark people. In fact, today's talk is about some dark states. And this is why I don't feel out of lab looking at the screen. So I will take like about 45 minutes if that's okay. Huh?
Yeah, it's
Sure.
fine.
Yeah.
Because I don't want to, increase the speed of my talking.
Of course. Yeah.
Yeah.
Okay, so I think we can start now. It's 11:37, I guess. Okay. So good morning, everyone. Welcome to today's Journal Club session. Today we have Dr. Ashish Arora with us. So Ashish did his PhD from TIFR and went on to do a postdoc from CNRS in Grenoble, France. And after that, he joined as a junior group leader in the University of Münster in Western Germany. And, following that, he is currently in IISER Pune as an assistant professor. So today's talk will be on dark and light bands in 2D semiconductors, which is probed by optical spectroscopy. So without much further delay, it's over to you, Ashish.
Thanks, Shomak, right? That was your name.
Yes.
Okay.
Yes.
Thanks, Shomak, for your kind introduction. It's very nostalgic for me actually to give this talk because we used to have this journal club when I was a graduate student in TIFR as well, and we used to give these talks. And I find myself still in the mailing list, and that was very a happy feeling to be in the mailing list of that journal club still. Even after this 8 or 9 years since I have done my PhD in TIFR, I left in 2013. In any case, so let me share my screen so that we can start with the talk. All right. So as you can see in the title, I will be talking about some optical spectroscopy investigations on two-dimensional semiconductors. And using this optical spectroscopy, we are interested in probing some Coulomb-bound quantum mechanical states called Trions and Excitons. We will slowly learn what I mean with this. Overall, my area of research, it concerns probing such states like excitons, trions, bi-excitons, charged bi-excitons. These are all these Coulomb-bound states, which can be created in two-dimensional materials. So this is a layered semiconductor. And then we apply very large magnetic fields of the order of 30 Tesla. And we see Zeeman effects or some other effects which are new. They're called valley coherence and polarization. I will not discuss them more, but they have some potential applications in the future technologies in the field of electronics. And then we also see Landau quantization effects in magnetic field or diamagnetic shifts, and we find various things like effective masses of carriers and so on. You can, if you are interested, you can check this perspective, which I wrote very recently in Journal of Applied Physics. This is about magneto-optics of layered two-dimensional semiconductors and heterostructures. All right. So today's talk will be divided into two parts. The first part will concern probing some excited states of trions. So there are these three particle bound states, Coulomb bound states called trions, and they can have excited states as well. So we wanted to probe them. There could be bound states and scattering states of these trions. And the second part will concern probing some dark trions, meaning there are these three particle states which do not interact with light. So they are dark. However, we can still see their effects indirectly on the optical spectra, and then we can indirectly find the energies of these dark trions in various materials. But let's start with some basics first, because as I understand from the organizers of this talk, that we have a diverse audience consisting of many backgrounds. Although this is a condensed matter physics audience, but it never hurts to go back to basics. some things can be very basic for you, but pardon me. So we know semiconductors, they have intermediate conductivity between metals and insulators. There are well-known examples, germanium, gallium arsenide, and silicon. The most important part is that the conductivity, it can be controlled by doping, electric field, light, and various other means. Let's place an electron in a semiconductor. Then we know from basic physics that it behaves as if it's a free electron, but it has a different effective mass m star, and we call it block electron. This is a quasi-particle. Now it's called a quasi-particle. Let's take the case of a silicon first. We want to know how bands come into picture. In the case of silicon atom, we have this outermost shell electrons in 3s and 3p shells. And then if we bring lots of silicon atoms together and try to make a crystal, we reduce the interatomic spacing. We see that these outermost levels or the outermost orbitals, they start to hybridize. And at the interatomic spacing A, which is the real crystal spacing where the silicon crystal is created to be stable, we have a conduction band and a valence band. Now the valence band is full, meaning the states are full of electrons, and the conduction band is empty at 0 temperature. We have something called an EK diagram, right? So the EK diagram, or in the reciprocal space, the energy looks like a parabolic in shape in the conduction and valence band, right? So there is an energy gap where there are no states available. And we know that the effective mass can be derived, if we know this EK diagram, by taking a second derivative of energy with respect to K. Just to remind you, typical band gaps of semiconductors lie in the visible to UV to infrared regions, starting from 0.3 electron volt to like 3 or 4 electron volts, typically in semiconductors. Now we will be talking about optical processes. In these optical processes, we have two types of processes. One is optical absorption, other is emission. In optical absorption process, you shine a photon on a semiconductor, take an electron to the conduction band, create a hole back, and the photon is absorbed. This is optical absorption. And this electron can fall back to the valence band, and we get photoluminescence. These are the most basic optical processes. Now the momentum has to be conserved in physics. Photon's momentum in this process compared to the crystal momentum is very small. In fact, it's 1,000 times, roughly 1,000 times smaller than the scales of crystal momentum. Therefore, this process is mostly direct. The initial momentum is anyway equal to final momentum, even if we do not consider photon's momentum into picture, because it's very small. So such materials where there is a lowest point of conduction band coinciding with the upper point of the valence band, highest point of the valence band, there is this direct transition. And if this transition is lowest in energy, such materials are called direct band gap materials. And these find profound uses in light emission devices such as LEDs, lasers, and so on. And examples are gallium arsenide, gallium nitride, and so on. So they are efficient light emitters because the momentum selection rule here is obeyed by this optical transition. So getting a photon out is easy. However, there are other materials which are in fact more popular, such as silicon and germanium, which are actually inefficient emitters of light because they are indirect band gap materials. The reason is the bottom of the conduction band and the top of the valence band for the lowest transition is an indirect gap. They lie at a different point in the valence zone. So you need a phonon, then only you are able to emit a photon. So this is a two particle process. So obviously this is inefficient. However, such materials find profound uses, as we know, in creating these processors of computers and also in photodiodes, in absorption-based processes, and so on. When we talk of optics on semiconductors, we always talk of optical joint density of states because this explains a large amount of physics of these optical processes. Let's take the case of a three-dimensional semiconductor and we shine a photon. We create this transition. This transition takes place in such a way that the joint density of states goes as a square root of E function. So if you go to higher in energy, you will see that the strength of this transition will start to increase. Okay, so this is a square root of E type of function. If we squeeze one of the dimensions of this 3D crystal, almost equal or on the order of Louis de Broglie's wavelength, H by P, then we get a two-dimensional semiconductor. A popular example is a quantum well. So around 1970s, these two-dimensional semiconductors, or the famous particle in a box problem, which was a theoretical problem until that time, that was realized in lab. What people did was they sandwiched some layer of low band gap materials such as a gallium arsenide between the barriers of high band gap materials such as aluminum gallium arsenide. Then you have a well here for electrons and a well here for holes. It looks like a barrier, but because holes are positively charged, it's also a well for holes. And then you should have quantization of energy levels. You cannot have continuous energies for electrons similar to a particle in a box problem. So there are these, I have shown 2 electron levels, 2 hole levels just for representative purposes. So then you can have 2 types of transitions here. And the point is that the 2-dimensional density of states is a constant with energy. So what happens is that when you hit this first transition, you suddenly have a step off in the density of states. And when you have the second transition, you have another step. So the density of state becomes double. The amount of states available for the photons to interact with per unit volume of the crystal gets doubled. So this is the difference between the joint density of states for a 2D material, which is compared to a 3D material. So what do we expect? If we now measure some absorption spectrum for a 2-dimensional semiconductor, then we should expect a step-like behavior for a 2-dimensional semiconductor, because this is how the absorption will keep on increasing as the light is hitting more and more resonances in the material, or more and more transitions, not resonances, transitions. Okay. However, this was just without Coulomb interaction, because now if we create electron hole pairs in a semiconductor, we have Coulomb interaction, right? So this Coulomb interaction actually leads to the formation of hydrogen atom-like species in a semiconductor, and these are called excitons. In fact, the spectrum of these excitons would also expect it to be similar to that of a hydrogen atom in the end. Now we shine a photon again, we create this electron hole pairs, and they are bound by Coulomb interaction with an energy equal to EB. And this Coulomb interaction energy will reduce the energy of this transition, because this is a bound state now. And this exciton will appear as a sharp resonance below the band gap, below the actual band gap. Actual band gap is EG. We can call this as an optical band gap. Some people call it optical band gap, E optical, where the exciton starts to absorb. Okay, so binding energy is then the normal band gap, which is the single particle band gap. We also call it single particle band gap minus optical band gap. And then this exciton can recombine and give rise to a sharp line in the emission spectrum as well. Now let's take a look at these binding energies EB. For a 3D exciton, meaning in a 3D material, the binding energies vary from a few MeVs to few tens of MeVs. If we compare it with the room temperature, which is of the order of 25 MeV, then we find that these few MeVs and so on, they would not be very stable at room temperature. So it's very difficult to study these excitons in most of the semiconductors at room temperature, because the binding energies are small. However, if you create a 2-dimensional exciton, just as in a quantum well, if you create an exciton, the binding energy is theoretically expected to be 4 times than that of the 3D case. So then it becomes more stable and it becomes easier to study 2-dimensional physics at elevated temperatures. So this is one thing we should keep in mind before I move on. So the point is, now these excitons would strongly absorb below the band gap. So they strongly modify the absorption spectrum. Let's see how they modify the absorption spectrum. Again, the case of a quantum well where some exciton is created. Theoretically, we expect that this should have an optical gap where there should be a very strong peak. This should be the excitonic transition. And then there should be something more. We will discuss about that. So this is a ground state of exciton, ground state of bound exciton, because just like in hydrogen atom, there are ground states and excited states. That is shown here. So an exciton itself has its own parabolic EK diagram. So you have a ground state, 1s state, which is expected here. But then you also expect this 2s, 3s, and so on, these excited state. Additionally, you also expect scattering states or unbound states of excitons as well, which start from the edge, the band edge, meaning where the binding, the binding of the states stop. That's the single particle band gap. So there you should start seeing some contribution due to the scattering states of excitons. Now let's zoom into this region. First, we discussed about this 1s exciton, which is a huge peak. However, if you zoom into this region, you start to see more. So this is, of course, first I should emphasize, this is expectation. This is a theoretical spectrum, not an experimental spectrum so far. So there should be a small 2s peak, then there should be 3s and so on. And then there should be this two-dimensional density of states step-like function, which should correspond to the scattering states. However, the scattering states also have some Coulomb interaction in them, so they enhance the absorption spectrum, and this is called the Sommerfeld enhancement. So without them, you will expect this, but with Sommerfeld enhancement, you will expect this. So it should fall a bit, in fact, while going to higher energies. So this is what we expect. These are expectations. Now let's look at the experiment. So this experiment was done actually in 2010 in TIFR. In Professor Arora's lab, Professor B.M. Arora. He then retired shortly. I did my master's thesis with him. Okay, so let's look at this. So this is this gallium arsenide quantum well. And then there are two types of hole levels present in this gallium arsenide quantum well. These are called heavy holes and light holes. Actually, these come into picture due to the hybridization of p orbitals, which make the valence band. And then you have one of the holes which has a larger effective mass than the other. So this is why that's called a heavy hole. So you can have two types of resonances called heavy hole exciton and light hole exciton. And if you measure the absorption spectrum, it appears like this. So there is a heavy hole exciton, there is a light hole exciton. And then you have this step-like function. One step comes from the heavy holes and the other step comes from the light holes. Okay, so these are the scattering state contributions. However, we are not able to see these excited states of excitons because they are supposed to be, first of all, very small in intensity. Secondly, we have a very broad line here compared to the binding energy. The reason is the binding energy is of the order of 10 MeV. So you should see all these states within 10 MeV. However, the line width itself is 5 MeV. So and the energy is, sorry, and the intensity is also small. So you do not see very easily all these excited states in a quantum well. Therefore, we have to look for some better materials to study such kind of two-dimensional physics. All right, so let's move on to trions. Now, similar to an exciton, you can have an extra electron added, and then you can have a 3-particle bound state similar to a H negative ion. So this is called a trion. Now we know this structure of an exciton. A trion should exist slightly below in energy compared to this exciton, because you add one extra electron and the overall energy of the state reduces. So this should be a trion, and this is the trion's binding energy. Such trions were first observed in 1990s, actually, in cadmium telluride and gallium arsenide quantum wells. For example, in the absorption spectrum, you see a peak just below the exciton's peak, and this is a trion peak. This is absorption, and luminescence also you see a peak. The binding energy of these trions is very small, 1 to 3 MeV. So you have to go to very low temperature. Here it's 1.7 Kelvin, because otherwise they will not be bound and you will not find them in the spectra. So this is much smaller than the room temperature. Now, what do we expect more? We expect that corresponding to these excited states of excitons, there should be another trion, because you can add an extra electron in this exciton state. So there should be another trion, but these have never been detected in any of the quantum well systems before this work. Similarly, you expect that there should be scattering states of trions, similar to the scattering states of excitons. So these scattering states of trions should start appearing from the exciton's energy, something like this. But these scattering states of trions have been theoretically predicted so far in the spectra, but they have never been observed experimentally in quantum wells. So this was our motivation to start looking for such species in the spectra of 2D materials, because the binding energies in these 2D materials are large. So this is why we come to now the real 2D materials. The field started with the exfoliation of graphene. We know that in 2004. However, graphene has no band gap. Therefore, the use for optics is limited. However, in 2010, MOS2 was exfoliated. A single layer of MOX2 has a band gap around 1.9 electron volt, which lies in the visible region. And then it has now a band gap, essentially. It's much thinner than the quantum wells, and it's an ideal 2D material now. In fact, most interestingly, the band structure is indirect gap in nature for bulk, but once you reduce to monolayer, it becomes a direct band gap material, and it starts to emit very brightly. For example, for a bilayer, you don't see much emission at all. In fact, on these scales, you do not see, but for a monolayer, it's very bright. Suddenly, you start to see a lot of light emitting out, because now it has become a direct band gap material. This was seen in 2010, and this is where the field kicked up. In fact, this paper, I think it already has more than 13,000 citations or something. I don't know. I will have to check what's the latest. Okay, so after that, there is a complete zoo of two-dimensional materials. Many of them are semiconductors, many are magnetic insulators. In this talk, we will talk about the semiconductors. Yeah, MOS2, MOSE2, WS2, WSE2, and so on. As I told, the excitons are very strongly bound in transition metal dichalcogenides. The binding energies are they are quite large compared to the room temperature. So one can easily expect to see these excitons at room temperature compared to the 3,5 semiconductors such as gallium arsenide. An example is shown here for a single layer of tungsten disulfide. So this is the absorption spectrum, and this is a very strong excitonic peak. So one can see that at this energy, a single layer of a material is absorbing almost 30% of light that's shining on it. So this is incredible to me. Just a single layer, which is 100,000 times thinner than human hair. Huh? And then we also know that the trions in these materials are also strongly bound. They have binding energies of the order of 30 to 50 MeV, and they appear as peaks below the exciton by 30 to 50 MeV. So they are also visible at much elevated temperatures compared to the 3,5 semiconductors. Here, the blue curve is the luminescence, light emission spectrum, and this orange curve is the absorption spectrum. So you can see two types of trions. We will see the reason why there are two types of trions in this semiconductor. But these two types of trions appear both in absorption and luminescence equally well separated lines. Okay, now let's come to the first part of my talk. Now, since the introduction was a longish one, but now I will be very fast because now we can go directly to the results. You know the basics. We will start with excited states of these trions. Okay, slight motivation. Hydrogen atom, we know that there are these energy levels. It was found that the H negative ion in the ground state is stable. This has been a well-known thing since very long, since many decades. However, it was found in 1977 theoretically that if you put one extra electron in the 2s state, then such a state is unstable. And this has never been seen either in experiments. So such states should appear here. So this is unstable. So this is also a trion-like state, H negative, but one electron is in 1s and one is in the 2s. So this is unstable. At the cost of confusing you more, if you have one extra electron in 2s state, meaning both electrons are in the 2s state, so such doubly excited states are found to be stable, both experimentally and theoretically. This is known from 1990s in the atomic physics. So we wanted to see if we can find similarities between this H negative ion and also in trions in the two-dimensional semiconductors. So let's try to find these in monolayer TMDCs. We have an absorption spectrum where there are these there A, B, and C excitons. There are three kinds of excitons which are visible. Let's not go into details of this absorption spectrum. This is a monolayer of tungsten disulfide. A sample structure is shown here, but this is not important. We have to know that this is a monolayer of tungsten disulfide. Let's zoom into this region. Then we see that there is this 1s exciton, the ground state exciton, which we have been discussing. And then there are two types of trions, which I also discussed. Now there is something more here. Let's zoom into this part. Then we see that there are two peaks more appearing. First of all, now after zooming in, we see a step-like function here, another step-like function here, and then two more peaks. So immediately it says that this has to do something with the two-dimensional material because there are these step-like functions. Let's try to identify these peaks and then let's try to pinpoint why we identify these peaks as they are at the moment. So we use just Lorentzians to simulate the bound states and then these step-like functions with Sommerfeld enhancement to simulate the excited states. So these are the trions. We know that already. So these are these 1s trions. This is the 1s exciton. Now there is a 2s exciton, which is visible here, the excited state of exciton, which was not visible earlier in a quantum well, the excited state. And this 2s exciton is this one, right? And after that, there are these scattering states of excitons, which are these shaded regions. They start from the band edge. After the band edge is somewhere there. And then we expect an excited state of trion, which is visible here. This is a doubly excited state of trion. It's visible here as a peak. But so far we have just identified this just by looking at it. But we need to find evidences if this is the excited state of trion or not. And then there is another step-like thing which should start at the binding at the position of the exciton, energy position of exciton, and this should be the Trions scattering state. All right. So we have seen many new things, but we have seen all those things which we had predicted in our spectra in this, but still we have to give evidence. For first evidence, we go to our Tretician colleagues who know how to calculate the spectra using GWBSE theory, which is essentially a density functional theory plus Coulomb interaction on that, plus some other corrections, free energy corrections on that. And then they find that in the place of where we are seeing Trions, there should be two Trions which are bound. And they should be 1s-like. The wave function is 1s-like. Probability distribution is 1s-like. However, just below the 2s exciton, there should be two types of Trions again, which should be bound, and the probability distribution should be 2s-like with a node, just like a hydrogen atom. So they beautifully calculated it, and this is quite convincing. However, we need more experimental evidence, because just looking at peak in any experiment does not mean anything. We have to do more. So for that, we go to a well-known thing, which we found in literature. In 1995, it was established that if you have a Trion exciton connected pair, and if you raise temperature, then the Trion starts to lose its strength, whereas exciton starts to gain for some reason, which I will explain. So essentially, for a connected pair, with raising temperature, exciton should gain strength, whereas the Trion should go down in strength. Why does this happen? Let's suppose we have this conduction and valence band, and we have some excess carriers, some extra electrons in the conduction band, which are required for the creation of a Trion. So then we can create some Trions and some excitons. Now the point is the following. For creation of a Trion, we are talking that there should be excess electrons in the center of the band, because it's the center of the band which is the most bright area, because that's where the photon has a direct transition, right? However, if the center of the band is completely filled of electrons and there is no empty state, then you cannot create an exciton, because for a creation of an exciton, you have to push an electron from valence band to an empty state in conduction band. So you need an empty state. So the strength of this exciton will be very low if you have a filled conduction band in some sense, right? So this is why at low temperatures, when the excess carriers are frozen in the center of the conduction band, you have lots of Trions, but less excitons. However, when you raise the temperature, you have a Fermi-Dirac distribution, redistribution of these carriers, and this takes it to higher energies. This spreads the electrons to higher energies. And then you have some excess states available, empty states available for the creation of excitons, but the Trions reduce now because you have less number of electrons now. So you should have an exciton which is gaining strength, whereas a Trion going down in strength. So this process is also called transfer of oscillator strength, because you have transferred the strength from one species to the other. And this is exactly what we see for the 1s states in our experiment. We have this low temperature experiment where we have a low temperature spectrum where we have two Trions and one exciton. We raise the temperature, Trions go away. They wash away, they lose strength. Whereas if you calculate the area under of the excitons, you find that their strength rises. The Trions go down and the exciton rise. So this is in line with what was discovered already in 1995. Now let's go to the 2s states. We see very similar thing. The 2s exciton, it rises in strength. I can even zoom into this. You can see that as I increase the temperature, it rises, whereas the Trion goes down in strength. So similar to 1s state, it rises and it falls. So that means the 2s states also show transfer of oscillator strength, which is another evidence that this has to be a connected exciton-Trion pair. One last piece of evidence is that these two are connected states, right? So that means that an exciton, if it captures another electron, then it can scatter to a Trion. It can become a Trion. So now if a scattering channel is available for the exciton to scatter to, for example, if a Trion and exciton both are there in the spectrum, then you expect a larger line width. Because if you have any scattering mechanism happening, then the line width is large. Okay. Now, when the Trion is losing its strength, you can see that the line width here is reducing, right? That means that these two states are connected, because now that channel to which the exciton was scattering back to has suddenly vanished and the line width has reduced. So this is actually very counterintuitive in semiconductor physics, that when you are raising temperature, line widths always increase. However, what's happening here is that the line width is actually reducing with raising temperature. So this is also a benchmark test that this is actually a Trion exciton pair. So what we have done is that we have found an evidence of an excited bound state of a Trion. We have found evidence of the scattering states of the Trions. And we find that the 3 particle states, they govern a wide spectral energy range in doped semiconductors. Because earlier these 3 particle states have been neglected, these scattering states and so on, but we find that they are just present everywhere. So this is what this work says. Let me quickly go now to the next part of my talk and the last part of my talk, where we detect the effect of some dark Trions which should not actually interact with light, but they still have a very strong effect on the optical spectra. So we find the effect on the photoluminescence of these dark Trions. There are some Trions which do not interact with light, and on the absorption spectra, and we find then the energies of these dark Trions. Let's go to some basics. Now, there are 2 types of this transition metal dichalcogenides or these monomers. One are tungsten based and one are molybdenum based. You can have tungsten disulfide, diselenide, MOS2, MOSE2, MOTE2. And theoretically, it was suggested around 2014 that the tungsten disulfide and tungsten diselenide should be optically dark materials. Okay, what this means is that the conduction band has a splitting that was said, and that the bottom of the conduction band has electrons only available with downspin, and the top and the second conduction band, the other one, higher energy one, should only have electrons with upspin. Okay, the spins can be inverted, but let's not go into details. The point is that if you want to make any transition in these two-dimensional materials, then the spins have to be preserved. Okay, but here the lowest state, which will be most occupied at low temperatures, would have an opposite spin compared to the top of the valence band. So therefore, this transition is not possible. Unfortunately, if the material is having such a band structure, this is not an efficient emitter of light then, because most of the carriers will be frozen at low temperature in this state, in this conduction band, and then you will not have recombination possible. So that's why these materials are called dark materials, because then they won't be an efficient emitter of light. However, in molybdenum-based materials, the spins are inverted in the conduction band, in the split conduction band. So this splitting is due to spin orbit coupling. And then this transition is possible, and they should be bright materials. Okay, so this was theoretically predicted, but then we experimentally verified in the coming years in these papers that this is actually true. And now this is the case of excitons. If we add an extra electron to create a trion, then the band structure becomes slightly complicated. Let's take the case of tungsten disulfide or selenide again. You can have 2 electrons here in the blue bands here. Now this makes a bright exciton because these are blue both. You can add an extra electron either in this green band here or in this blue band here, or you can have another kind of state. Okay, let's take a look at the first at these left 2 states. So these 2 states are actually bright trions. The reason is that the selection rule comes from this excitons. Yeah, so there are these 2 spins which are the same in same direction. So this is a bright exciton, and then you can add these 2 extra electrons, one in here, one in here. Then you have bright trions. So that's why you have these 2 types of bright trions. However, if at the same K point of the Brillouin zone, you have an upspin in the conduction band and a downspin in the valence band, then this is a dark state. Then this is a dark exciton. Then you can place another spin somewhere, and this will be a dark trion. So the point is that this dark trion has the lowest energy in the spectra of this tungsten-based material. Therefore, they would dominate the optical properties, because now they are the lowest energy. They would freeze every carrier possible at low temperatures, and they would start dominating. The problem is that they do not interact with light, so they are very difficult to probe optically. There have been only very few works so far. But how do we understand their effect on the optical properties? Let's see. And we want to know which materials are bright and which are dark among these. Okay. Now let's measure photoluminescence as a function of temperature. First, what do we expect? Let's suppose you have 3 trion states. One is dark state and 2 are exciton. 2 are these bright states. And then the trion is a fermion now. So there is a Fermi-Dirac distribution possible just within the trions. Once the trions are created, they will have a Fermi-Dirac distribution. And then you have a So these higher states, which are bright states, they will be less populated with the trions because they are at higher energy, and this state will be more populated. So you can expect a little bit of emission. But once you raise the temperature, the emission should rise. Now, this is also sort of counterintuitive in semiconductors, that the emission would rise as a function of temperature, because the emission generally falls when you raise the temperature, because you increase the number of photons, and then the two particle processes contribute more, and so on. But let's suppose there is this Fermi-Dirac distribution of these trions. And this is what it would lead to. It would lead to increase of light. This is what exactly happens for the photoluminescence. So the top graph is now, the top plot is at 5 Kelvin, and then we are increasing the temperature here. Let's only look at the trions part. You see that as the temperature is increased, the trions are rising in intensity. So this is what happens actually. There are two types of trions. One is blue, one is orange here. So first the intensity falls slightly and then it rises. Similarly for orange also, then it rises and then it falls. Now the problem is we have been expecting that the intensity just should rise, keep rising according to Fermi-Dirac distribution. But why does it fall? Actually, the fall comes from another term, which is the oscillator strength, which is about how many photons are actually getting absorbed also to create these trions. Yeah. So this oscillator strength can be calculated, can be actually found just by measuring the absorption spectrum as a function of temperature. And if this oscillator strength falls very rapidly, then we will know that this fall can be explained. Because there are two terms multiplied. One is the population, one is oscillator strength. Let's see the oscillator strength. Essentially, we have to measure absorption spectrum. We have to look again at this region of trions. We are raising the temperature and we see that the oscillator strength falls for both of these trions for the reasons which we had discussed earlier. We had discussed this, so I will not go into this again. So one can fit these oscillator strengths with a phenomenological function, which looks similar to a Fermi-Dirac-like step-like function. One can fit this. And once we fit this, we introduce this function here, and then there is only one free parameter left because this function is coming from the experiment itself. So this parameter left is now just the energy separation between the bright and the dark exciton, trion, bright and dark trion. So if we fit these spectra now with this function, with this number, then we find that this number turns out to be 19 MeV. And these spectra fit very beautifully actually. In fact, this small fall in the beginning is also reproduced and then it rises and this falls. So this is just a single parameter fit essentially. And we find that the dark trion state in tungsten disulfide should be 19 MeV below the bright trion state, the lowest bright trion state. In fact, this has been verified in another work where they measured the dark trions with some specific method by applying large magnetic field. Directly they measured the energy and they find it is correct. It's 19 MeV. So it's exactly the same. Finally, we do the same thing for other materials. For example, for tungsten diselenide. Yeah. And we find that there is in tungsten diselenide also, everything works with 19 MeV below. Yeah. For MoSe2, we find everything works with 6 MeV above now. So the bottommost state for MoSe2 is a bright state by 6 MeV and the dark state is above. For MoS2, it's very complicated. It's almost a mixed state. So within 2 MeVs, bright and dark states, dark trion states, they lie very close to each other. So summarizing, essentially, we can create a picture here where there are these excitons, and then we can have these trions below the excitons, and the dark trions are the lowest in energy for tungsten diselenide and tungsten disulfide. For MoSe2, the bright trion is lowest in energy, and for MoS2, this is almost like a mixed state. They are very close to each other. So what we prove here is that a Fermi-Dirac distribution of the combined population of dark and bright excitons, it governs the PL and absorption of two-dimensional materials. MoS2 possesses a mixed bright-dark character. So in summary, we have been discussing about the ground and excited states of excitons and trions. An excited state of trion was found, and the scattering states of excitons and trions were found to exist. Then we discussed about absorption and emission processes as a function of temperature in the doped semiconductors. And we find that we can obtain the dark trion energy from these temperature dependent optical experiments. And these dark trions are the lowest in energy in tungsten diselenide and sulfide, and they are higher in energy for MOSE2. For MOS2, it's a mixed state. Okay, so the experiments were all done in University of Münster in Germany with my colleagues here. And we had collaborators in France, in Grenoble, and in Poland. Thank you for your attention.
Thank you, Ashish, for the nice talk, actually. So it was very smooth. And thanks for your time in this early morning on Saturday.
It's all
And
right.
so now we are open to questions. If anyone has questions, please feel free to ask. In the meantime, let me start with one of my questions. So you said about electron-electron correlation. So
Yes.
experimentally, can it be detected? Means what's the magnitude of this electron-electron correlation interaction?
No, electron-electron correlation in what?
No, in these Trions and excitonic states, we have
Yes.
these electrons being correlated. So means can the Coulombic interaction energy be extracted by some experiments?
Yeah, so this is what we are doing actually. So you have these two trions which appear below this exciton state. So the energy difference between this exciton and this trion state will exactly be that electron-electron correlation interaction energy.
Yeah,
so this
true.
is the binding energy of trion. Yes.
True, true. Yeah. And as you increase the temperatures, this PL in the photoluminescence peaks. So
Yes.
this of the excitons, peaks of the excitons also shift to the left in energy. So why is that?
And
yeah, means what why is it's shifting to the left in energy, means to a decreased energy scale.
Right.
If I increase the temperature. Yeah.
Right. So there are essentially two kinds of effects which are responsible for this redshift when the temperature is increased. One is that the number of phonons is increased when you increase the temperature. And then there is an interaction between these excitons and phonons. This interaction leads to this reduction of energy. And secondly, the lattice expands when you increase. So when the lattice expands, you have a reduction of this energy.
I see. And also, like in the beginning, you said that you apply something like 30 Tesla or something to some magnetic. So how do you do that? Is there specialized labs for that?
Yeah, exactly. So essentially, in Grenoble and in Nijmegen, Nijmegen is in Holland, we have two laboratories where we actually have large powerhouses, large as in 24 megawatt of powerhouse, which is just used to power one magnet. So you can think about it like a Rajdhani engine is like 4 or 5 megawatts. So you can have like many of them connected together in parallel, pushing a magnet. In fact, I think I have some picture. Yeah. So this is the picture of a magnet here. And you see that you need 64,000 amperes of current at 400 volts to run this, to power this magnet. And you need a water cooling of 300 liters per second. So I have not put a human here. If I had put a human here, human would be of this size. So this is a very huge magnet in that sense. Yeah, so this is how we generate large fields. Now, since you have asked this, let me tell you one more thing. You can even have very much larger fields, such as 200 Tesla or even 1000 Tesla and so on, but for very small amounts.
Small times, yeah.
Yeah, so there you just have a single coil, for example, a single copper coil. You push lots of energy by discharging a capacitor bank within a few milliseconds. And this coil, because of the Lorentz force, it explodes. So one can actually see, okay, let me share the sound. One can actually see in this video. I hope this works. This is in Japan. They are so happy at this explosion.
So is this sufficient to do your kind of measurements? Like if let's say it is only millisecond or few seconds, it gives 210 Tesla. Means...
Yeah, so for my measurements, where I need very large signal to noise ratio, This is not very nice. I mean, one can do that if one has very large, very fast CCDs for acquiring spectra and lots of light, because then one can acquire maybe one spectrum in 1 millisecond. So within 10 milliseconds, you acquire 10 spectra within this shot, and then you average them out, and then you then you can have one spectrum. But it's not very convenient, because after this one pulse, then you have a preparation time of, I don't know, many hours, and then you have the next pulse available.
Yeah. And since we are already talking about Trions, so is there like electronic states, like let's say 4 species coming together, 1 positive and let's say 3 electrons?
Oh, that state with 1 positive and 3 electron states, theoretically, my colleagues find that they should be unstable.
Oh, okay. So
Yeah.
anything above Trion should be unstable, is that it?
No. So the bi-excitons should be stable. Let me go to this slide.
Excitons.
Yeah,
Okay.
so if you have 2 positive and 2 negative, then this should be stable.
I see.
So this is like a helium atom, right? And then a helium negative atom should also be stable, a charged bi-exciton. In fact, we also see this very regularly, very readily in our experiments. I am not showing that data in this.
I see.
Yeah.
Means the intensity is very low, or it's like similar to Trions?
Oh, so actually for creation of a bi-exciton, you have to create a very large population of excitons to begin with. So you need very intense pulses of light. So those are a completely different regime of experiments where you have pulsed lasers for exciting the sample. Within a very short pulse, you have lots of photons, and then you create such large bi-excitons and charged bi-excitons.
I see, exciting. Nice. Yes, anyone else, if you have questions?
Yeah.
Yeah.
So the last slide of your introduction.
Yes. Oh, it's a longish introduction. Now I realize.
Yeah, this one. Yeah.
This one.
Yeah. So why we can see a PL peak at like exciton PL peak here?
Oh, so there is this exciton PL peak. It's a very small peak. First of all, this is a dark material. This is tungsten disulfide, and this is a low temperature spectrum. So then most of the PL is coming from low energy trions, and in fact, lots of PL is quenched because there are dark trions and dark excitons as well. The dark excitons also appear somewhere in this energy region, which I have not shown.
And another thing is I didn't understand actually this transfer of oscillator strain theory.
Okay.
Can you please?
Yeah, let's go to that. Yeah. So let's take the case of a doped semiconductor. So there are some electrons available, some excess electrons, which will be in conduction band at certain temperature, right? And then there is a valence band. Now, if you want to create trions, then you need these excess electrons, because a trion is a 3-particle state. So then you can create some trions. But if you have these electrons which are frozen at the center of the band, then the excitons are very tough to create, because for creating excitons, you need an empty state here. You need an empty state here. This is this. Then only you will be able to excite an electron from here to here and create a hole. However, now that is frozen. So you create less excitons and more trions at low temperature, right? However, when you raise the temperature, you have this Fermi-Dirac redistribution of electrons within this band. So then you create some empty states here, right? So you can create more excitons now and less trions. This is the only thing. This is the transfer of oscillator states.
But it should not be, it's only valid for doped sample. For undoped sample, it will not happen.
No, because you will not have trions at all. Yeah.
But even if we have, so this will not follow this trend. So exciton will be larger and trion will be shorter, and with energy trion will go down.
No, again, sorry.
So even if it's undoped sample,
yes.
Even if we have a small trion signature, so with temperature, trion will go down and exciton will go up.
That is true. I mean, but in undoped samples, you cannot have trions at the first place. Whenever you have any trions, that means that there is some unintentional doping. Yeah, but this will happen then. That is true.
I have one question.
Yes, Vilas.
What kind of dopant using in 2D materials, 2D TMDCs
Correct. So
for
at
that?
the
Yeah.
yeah, so at the moment, doping these 2D materials has been challenging. People have been trying various things in their
Yeah,
processes by which they are growing. However, what we observe in our experiments is that our samples are unintentionally doped, meaning they during the growth process there have been some impurities in the sample which we do not really know about, and they are unintentionally doped. The doping density is of the order of 10 per 11 per centimeter square sometimes. Yeah, so this is not really clear.
yeah. And is there any possibility if your material is not means some defects is present in your material? So how you can say this thing happen due to doping or due to the means defects in that materials? So
Yeah.
how you recognize this thing?
Yeah, so essentially the oscillator strengths of various signatures due to defects, that is always very small, always. So you will not see the effect of defects normally in absorption spectra. You will see them in luminescence spectra. So this is what people see as well. There are some defect based peaks in some materials which are very low in energy, and they appear only in luminescence. However, this is not a bulletproof case of what I am trying to say. The point is the bulletproof tests are the following: that if something is due to trions, meaning something is due to doping, then only you can create trions. Then you should be able to have a consistent picture throughout due to trions. And the consistent picture means you apply some gate voltage, you should be able to increase the doping, and then the trions peak should behave in a certain way. They should redshift, maybe they should increase in intensity, exciton should vanish, and so on. This has been seen over and over in our lab also. And also you should have all of these things which I have shown you, like you should have this transfer of oscillator strengths, because then only you can have these connected exciton trion states with large oscillator strengths and so on.
Thank you.
Hi Ashish, this is a nice talk. I am Shurajit. I have a few questions.
Yes.
That is, one question is that it is a basic question that I still not figure out how it. If you give me a certain clue that you shown that in a two-dimensional, if you go that your bound state energy is increased by a 4 times factor.
Correct.
So how one can understand physically this dimensionality effect on that? If I go to the one dimensional, does it increase by even more?
This should increase even more. So the only thing is, like, you have some state which is now confined to certain volume, right? So once you confine certain state to some lesser volume, it will have a larger binding. So this is how you expect to happen it physically. And if you have a 0D state or a 1D state, then you should even have larger binding energies.
Okay. The second question is mine, that in this same slide, it is a large range of magnetic field. Your peak is not shifted. And
no, there is no magnetic field here.
Huh?
There is no
it's with temperature.
Yeah.
Up to like 110 Kelvin.
Yes.
There is no shift in the peak. After that, it starts shifting. So it's like almost temperature independent.
Yeah. So the thing is the following. There are two types of phonons. One is acoustic and one is optical, right? Acoustic phonons normally do not interact very strongly with excitons. And acoustic phonons are excited normally around 100 up until 100K, from lower temperature until 100K. And after that, the optical phonons take over. And optical phonons, they interact strongly with excitons. And once they interact strongly with excitons, you have this redshift. So this redshift is due to interaction of excitons with optical phonons largely. So this is also called polariton shift, by the way.
Okay, polariton.
Yes.
Okay.
Yes.
The last question is in the summary slide. Actually,
yes. Let's go there.
Yeah. So if I see that the dark trions in energy determinant up to the two curve you are showing. So in the this orange one, yes. If I look it very closely, it seems like there is a two peak.
Two peaks
means where? One is going up, then go down, and then going
here.
Up.
Here.
Yeah.
Oh, this is just
is it a two peak or is it just a single peak? Even in the blue curve also, if I look it very closely, so one is going up, then it is going a bit down and then go up.
Yeah, so actually this is experimental error. The thing is the following. How this curve is obtained is by measuring the absolute intensities in the experiment. So now to measure the absolute intensities, you can have lots of problems, meaning first you have to maintain the same excitation intensity of laser, and then you obtain some spectrum, and then you take an area under the curve, which will have some inherent error. The other problem is like the spot on which you are exciting in your sample. It has to be absolutely the same. If the spot moves a little bit, the intensity changes. So this is actually an intensity, luminescence intensity. And we have repeated this experiment many times. In fact, this curve is an average of a few experiments which we have obtained. And what we see is that in some of them, you will have this point here, in some of them you will have there, in some of them middle, but this is the average. So, but there is nothing here really. That's what it does not reproduce.
Thank you so much.
You're welcome.
Yeah, another maybe naive question.
Yeah.
Is you showed the different kind of transformation, like darken and bright.
Yes. Yeah. Here, right?
Yeah. So I was just thinking, so in the lower one,
Yes.
so like electron from one valley and the other electron from the other valley.
Correct.
So how is it possible, I mean, physically that, I understand for a same case it can be Coulomb bound,
Yes.
but it's Coulomb bound with some other electron from other valley.
Sure, definitely. So this is what, I mean, if one tries to think at it physically, this is very difficult because this is a quantum state. This is a quantum state of three particles having different k vectors, right? So this is very difficult if we start to think about different velocities and so on. This is very difficult. However, it is known that the indirect excitons and indirect trions, they create this bound quantum state. And this is, I mean, quantum mechanically, this is allowed. I'm not sure how to explain this intuitively.
My conclusion is like how exciton created in one valley cannot scatter to the other, right? Due to the conservation, they're fixed to that valley. So they need a large phonon pathway to go from
Correct.
one valley to other.
Correct.
But if that is not possible, then how one can, I mean, couple to some electron in the other valley?
No. So for coupling an electron, you don't need a phonon from the other valley. For scattering, you need a phonon. That is true. The point is, I mean, if you have these two electrons in different valleys, you can of course scatter between them, and that is an exchange interaction. And that might include phonons. But for creation of a state as such, you do not need any phonon to begin with, because the selection rule says that the photon excites this point at this point. And if there is an extra electron around somewhere, that can just come and attach to it. You don't need a phonon to create this state. So you can create this three particle Coulomb bound state just by following the selection rule of the exciton. At least this is what my understanding is after talking about this to various statisticians.
Yeah, so I have a small doubt following the Deepa's question.
Yes.
That in the first, as you were telling that if the lower band has a opposite spin, then we have a dark trion.
Yes.
So, but in the fast diagram,
Yes.
in the right side,
Yes.
so the lower band has a opposite spin. So
Yes.
still it's a bright trion. Why it is so?
Because there is also an electron available there in the upper band, which has the downspin. So the transition, the optical transition will follow the selection rule of this blue. And then you can have an electron there in this valley, which will come and connect and form this bound state. So transition selection rules come from this, from the blue bands.
Okay, thanks a lot.
On the other hand, on the right side, your question is very valid, because here you have no electron which is at the same K point. So if you want to really create this kind of trion, you need a phonon. Yeah. So you have to first create this state, this exciton. Okay, this is not how it works, but the selection rule has to follow creation of this exciton, which would need a phonon. And then you can have this extra electron. So this is why it's dark. It's dark due to phonon, due to the requirement of a phonon.
Can I ask like one question?
Sure.
So, can we get the phonon information in the absorption spectrum? I mean, in what energy range we can maximum probably get these phononic peaks?
Yes.
So is it?
Yes, definitely. So I have not shown that data, but let's go there. So essentially what happens is that you have a redshift of this line, right? And this redshift is due to phonons. Now there are some specific models available in literature using which you can model this redshift as a function of temperature. And there is a parameter of phonon energy. So you can find after fitting this, the energies of phonons.
I mean, is this the Lorentzian fitting or some other?
No,
In the interband transition, we get Dude model to fit some of the parameters. I'm not quite sure, but it might be possible that it's a combination of some two functions or something.
Yeah, so that Dude model comes from metals, but this is an interband transition which has a band gap. And this also is an exciton. Now, exciton is a Lorentzian if there are no other processes involved. So this is a Lorentzian independently, but the behavior as a function of temperature follows some other models. One is called Varshni model, other is called O'Donnell model. Yeah. And then the line width also increases, and line width is also increasing because the exciton is interacting with phonons. So this is also exciton phonon interaction, and that has another model called Rudin's model. And these three models can be used for determine the energies of these phonons.
Okay, thank you.
Well,
okay, I think if no one has any more questions, we can give a virtual clap to Ashish for this nice talk. And we expect to see him sometime in TIFR when things is, and it will be a nice interaction in face-to-face. So thanks again, Ashish, for this wonderful session, and we will close now and expect you to give more such splendid talks in near future.
Thanks. Yeah, I'm looking forward to that. Bye.
Thanks. Bye, everyone. See you next weekend or sometimes else. We'll keep in the loop in the email. Okay, thank you. Let us close. Thanks.